So thank you again for your patience. Thank you for being understanding. I'm working to dig myself out of being overcommitted. So today what I would like to do is wrap up our coverage of clustering and kind of the related topic of dimension reduction. Principal components, cluster analysis. These are both unsupervised learning techniques. And I've mentioned in passing that there's some additional things I wanted to touch on. For example, correspondence analysis. Correspondence analysis is a PCA-like method for categorical data. PCA is great if you have a bunch of columns of numeric variables and you want to summarize. But what if you have columns full of categorical data? There is a very similar technique involving eigendecomposition that we can do to discover structure and core relationships, core patterns in the data. So I want to show you an example of that today. I want to tie a bow on the material we've done for cluster analysis, just to kind of review it, the big picture of hierarchical versus k-means clustering. And wanted to touch on the technique that was actually in your homework, but that I will not grade this time, called multidimensional scaling. I said this a moment ago, but there's this general technique of ordination. Ordination is a kind of an umbrella term that refers to kind of the dimension reduction problem. You have too many variables, you want to force it down to a smaller number of variables. You're either interested in doing that for modeling purposes. You want to build a model for some response, but you have too many predictor variables, so you want to limit your attention to a smaller number. Or, like we've done with principal components, you're just trying to learn about the essence of the data. So if it's really high dimensional, you can't really visualize it, but if you can represent it with a lower dimensional framework, maybe you can learn about structural relationships. So correspondence analysis is another flavor of ordination. It's basically, let's take a bunch of categorical variables and cram them down into a smaller dimensional representation. But the benefits and the insights are similar to PCA. And multidimensional scaling, similarly, is a dimension reduction technique, or there's ordination in the description of it. But it operates a little bit differently from the other techniques we've seen. Multidimensional scaling, in particular, is driven by distance calculations. So in some sense, multidimensional scaling is a hybrid or an in-between of PCA and clustering. PCA is all about a covariance matrix or a correlation matrix and decomposing it. Clustering is all about distances, who's closest to who. Multidimensional scaling is kind of like ordination. Let's reduce the dimensionality, but we do that exercise with respect to distances, not with respect to raw values. So it's kind of a specialized application. I want you to at least have seen it. It's not used all that much in practice, I don't think, but it is nice to have as another technique or tool that you might use in an appropriate situation. Okay. Brief overview of the clustering routine. If we have the goal of clustering, let's say we have data n by p. Clustering, as we've said, is grouping one of the margins into groups. Either the rows, which is the individuals, grouping the individuals, or the columns, the variables. So we can either group individuals or the variables. There are a few different flavors of cluster analysis. The two main ones are what we've focused on, hierarchical and k-means. Hierarchical is the dendrogram tree-based representation. So for example, we start by saying that every individual is its own cluster, and we start working our way up, joining individuals who are really close to each other. Step one is which of the two individuals out of all the pairs is closest. Let's put them together. And then let's recompute distances and join again, and recompute and join again, until we've gone all the way up from everybody's their own cluster to one giant cluster. K-means clustering is a totally different algorithm. Both of them are trying to discover groupings. So they're both like aimed at the same problem, but they're different algorithms, which means they operate differently. They may give different results depending on the situation. But the idea of k-means is a very simple idea, and that is to group individuals. Let's say we're clustering individuals. It is to group individuals into clusters within which, again, the distances are smaller than they are without. The way it proceeds is, depending on the algorithm, we might randomly allocate some what are called centroids to represent clusters. If I have p numeric variables, then let's say we're going to go try to find two clusters. We could say cluster 1 has an average value, an average vector of such and such. Here's p numbers. That's the center vector or the centroid of cluster 1. And the second cluster is a different average. That's the centroid, the center vector of cluster 2. Then my clustering algorithm would say, for an arbitrary individual, compute the distance between that individual and those two centroids. Which centroid, which cluster is that individual closest to? And that's where I cluster them. Individual I is put into group 1 because it's closest to the typical vector of responses for group 1. The way k-means works, you can think conceptually, is randomly first put these centroids out there. If I'm going to do k equal 3 means clustering, you have to specify k, by the way. Let's go find 3 clusters. Then we might randomly pick 3 separate locations to temporarily put flagpoles as cluster centers and assign all the individuals based on which cluster center they're closest to. What you can then do is recompute the centers of the clusters that you just created. Let me draw a picture to kind of illustrate this. Easy to visualize in the two-dimensional case. So here's variable 1 and variable 2. Here's the scatter plot of all the data we have. And the k-means algorithm might initially say, let's randomly put a class or a cluster centroid at that red dot and put another one over here at this green dot. Then at this stage, I'm going to group or cluster all these individuals together because they are closest to the red dot, and I'll group these individuals together because they're closer to the green dot. Step 2 is then to recompute the centroid. The first location of this centroid was arbitrary, or it might have been random. And after having grouped people according to it, the new center of those grouped individuals is a little bit different. So the centroid gets moved or adjusted. This centroid gets moved or adjusted. And then we do the same thing. We ask for every individual, which of those two are you closest to? And that's how you cluster at step 2. Then recompute the cluster means, or the centroids. Do it again, do it again, do it again. And you keep going until it does not change anymore, until nobody gets reassigned. And then that's your clustering. So if I asked for clustering with k equal to 2, it's going to iterate around finding center points and assigning individuals to each of the groups until nobody moves anymore. So that's a totally different algorithm from hierarchical clustering. What I recommend in practice is use clustering because it's very useful. And because there's no one right or perfect algorithm for clustering in a given situation, try at least a couple of ways of doing clustering. Typically, if I have data, I do hierarchical clustering and I do k-means clustering. I'll do hierarchical clustering and make the dendrogram. I'll make a scree plot to decide how many clusters do I think there are. Based on that, so suppose I do hierarchical clustering and I look at a scree plot, I see an elbow at a place that suggests 3 clusters. Then let's go do k-means clustering as a secondary way of grouping. And based on the hierarchical clustering, it looks reasonable that there's 3 clusters. So I might do k-means and ask for 3 clusters. And then what you can do is compare between the 2 clustering methods. Ideally, they largely agree, but there are some cases where they will have some substantive differences. Neither of them is, quote, right or wrong. They're both valid ways of discovering grouping. So best practice would be to try both of them and then try in summarizing what you find to characterize a consensus. Hierarchical clustering and k-means both tended to put these types together and those types together. The details may be a little bit different. There may be some individuals that are classified differently according to the 2 algorithms. But because you don't have any reason to think that one of the methods is better than the other across the board, you want to kind of aim for a consensus interpretation. The other common technique for clustering that we're not going to get into is model-based. And that is, suppose, for example, that we were to say the data that we observe is the result of a mixture of k different probability distributions. For example, if we had height of human beings, if we went around campus and we recorded height for a bunch of randomly sampled people, we might see a bimodal distribution, maybe, where women tend to be shorter than men. There's like 2 subpopulations or 2 distributions that are mixed together. For a problem like that, where you think your data are the result of drawing from a mixture distribution, you can use things like maximum likelihood to essentially cluster. If we think that there's this type of distribution, suppose we have an individual that's right there. The clustering exercise would be, which of the 2 groups did that individual come from? In this case, a sensible thing to do would be to say most likely it came from this group because there's more probability at that point for that group. So imagine this mixture picture is kind of this that's going on. There's two distributions that are overlaid on each other. That red X could have come from the red distribution, or it could have come from the green distribution. It's more likely it came from the red distribution because there's more probability centered there for the red distribution than there is for the green. A model-based clustering algorithm kind of goes through that rationale. Let's assume a mixture distribution. Let's use a maximum likelihood algorithm to estimate the parameters of the mixture, and then we'll classify or cluster individuals based on which of the discovered groups it's most likely it came from. Clustering at the end of the day is unavoidably subjective. You have to make decisions about things like how do you define distance? What do you do about the linkage calculation? Do you use the average or complete or single linkage? What clustering algorithm do you use? Should you use hierarchical or k-means or model-based? Those are all things that don't have perfect answers, and the results may differ some depending on how you answer it. So I would encourage you and caution you not to try not to overinterpret the result of clustering. I would encourage you to be conservative also when interpreting clustering results. What I mean by that is be careful about overstating discovered groupings. When you do hierarchical clustering, for example, it groups everything together. As you go up and down the dendrogram, eventually you group everything together. So depending on how much attention you give to the dendrogram, you may wind up with claiming there's 2 clusters or there's 20 clusters. Be conservative in the sense that tend toward fewer rather than more clusters is, I think, the safe bet. In the video I posted last week where I went through simulated data, I had a few simulated data sets that we applied clustering to just to illustrate what can happen. One of the illustrations was there's no clustering whatsoever. We have an n by p matrix of numbers, and there is no association between the individuals. There's no grouping of them at all. If you take a data set like that and throw a clustering algorithm at it, the algorithm will still come back and say, here are the clusters we discovered. That's what the algorithm does. It finds clusters. So it's up to you to qualify like how much evidence there is to support the discovered clusters. So if you don't recall that, go look at the cluster simulation script that I have and run through that. When there's no grouping, you can still do clustering, but you need to be able to recognize in a dendrogram or a scree plot what it looks like when there's not any grouping. You need to be able to recognize what a real grouping looks like as compared to an arbitrary grouping. Because there's no guarantee in a given data set that there is any grouping or how much of it there is. When in doubt, is there, in my data set, 2 clusters or is there 15 clusters? When in doubt, I recommend be conservative. That means side towards smaller numbers of clusters. The more clusters you claim that there are in your data, the more likely it is that you're finding spurious groupings, groupings that don't really generalize. Clustering is subjective. It'll differ a little bit from method to method, so it's not really sensible to overinterpret a dendrogram, for example, and say, I think I have 8 clusters based on this kind of minor grouping in the picture. Try different methods, be conservative, don't overinterpret with clustering. All right, let's go look at multidimensional scaling briefly. This is slide 75 in the topic 8 notes. And I don't want to go through the algorithm in detail, but I'm just going to kind of describe this conceptually. Multidimensional scaling is a grouping or clustering algorithm that works from distances. So it's actually an ordination method that works from distances. It's not strictly a clustering algorithm. So suppose that you have distances. In some data sets, that's the data that you have, is distances. Not numeric variables that you can compute distances from, but distances. For example, longitude and latitude measurements for a bunch of airline destinations. The data I have are geographical locations. The idea of multidimensional scaling is to take data about distances and reproduce them or represent them using a smaller number of variables. Let me show you an example. I have an example in here, I think. Yeah. So here's an example, slide 82. And the nature of these data is such that distances are what we have in our, that's what we have. The essence of our data is distances. We have a matrix of distances between pairs of U.S. cities. So Atlanta, Boston, Cincinnati, and so on. And all these numbers are, I think, distances in miles between the cities. Distance between Atlanta and Boston is 1,068 miles, for example. There are 12 cities here. 12, in a sense, 12-dimensional data. What would be handy is if there was a meaningful way to visualize this information in a lower dimensional space. For example, two-dimensional space. Can we take distances on 12 locations and make a picture that essentially visualizes this information in a small dimensional representation, like a two-dimensional picture? So we get something like this. This is the result of doing multidimensional scaling on those distances from the previous slide. This is a two-dimensional representation, scatter plot, of those 12 variables, or 12 cities. If you look at the picture, it looks an awful lot like the U.S. Map. Boston is in the northeast, Spokane, Washington is in the northwest, LA is southwest, and so on. But this was not determined or mapped by longitude and latitude. There was no map behind the scenes to create this picture. This is an algorithmic representation. You tell me the distances between all the elements, and the algorithm will find a lower dimensional picture. In this case, a two-dimensional picture. So this is like taking all those cities, all those 12 cities, and projecting them down to a two-dimensional view. So this picture maintains the essence of the interrelationships that were in the original data. Boston is further away from Spokane than it is from Columbus, for example. That was one aspect of the distances on the previous slide. It's roughly equidistant from Spokane as it is from LA and from Tampa. So if you were to go back and look at the distances in the matrix, you could verify that those numbers suggest what I just said. Boston is further from Spokane than it is from Columbus. Go look at the numbers and that's true. Boston is roughly equidistant from Spokane and LA and Tampa. Go look at the numbers and that's true. So this is a computational way to create a meaningful visualization of data about which you have distances. There are some applications where this is a natural way to summarize your data. I will say it's not as widely used at all, not nearly as widely used or prominent as things like principal components and cluster analysis. But I want you to have at least seen it and heard of it. Multidimensional scaling, it's an ordination technique. It's all about distances and cramming a bunch of distances down to a low-dimensional representation. Think of it conceptually like creating a map. We oriented these cities with respect to each other just using distances, and what essentially we did was orient them on a map, because this is just like the map of the U.S. if you were to overlay the U.S. Picture. The other thing I wanted to lecture on a little bit today, or at least illustrate, is the correspondence analysis. So for doing that, what I would like to do is just show you an example. And the data I'm going to use are the DIY data, do it yourself. So these are DIY.csv from eCampus. Suppose you work for Home Depot or Lowe's and you have this database of customers. For each customer, so each row is a customer. These are people who have come into your store and purchased things at one point or another. And these types of data exist in the real world. Home Depot, for example, has millions of records in a database about your gender, about your socioeconomic status, your ethnicity, your purchase patterns, all that type of stuff is recorded. And so, of course, they would like to look at that data and learn anything that they can about their customers. That allows them to customize their advertising, to basically monetize better, make more money if you understand your customers better. So here's a Home Depot data set, let's pretend. Each row is a customer, and what we have are a bunch of, well, 5 categorical variables. These are categorical variables. Categorical just means it doesn't make sense to do arithmetic on the variable. Most of the time that means it's not numbers, although there are some categorical variables that are represented by numbers, like zip code. But it doesn't make sense to talk about the average zip code between College Station and Bryant. So just think, does it make sense to do arithmetic? Here's 5 categorical variables. We have a work variable, and this is a characterization of what type of profession each individual is in. Is it a skilled or an unskilled job? I don't know how they define that exactly. But presumably, flipping burgers is an unskilled job, and carpentry and medicine and stuff are skilled jobs. We have a variable called tenure that is about do you rent or own your home. We have a variable called DIY, and this is an internal designation for customers. Yes or no? Is this the type of customer who buys stuff to go home and work on their home themselves? DIY is commonly a abbreviation for do it yourself. And that's what Home Depot and Lowe's are all about. They want to sell you things, tools and paint and equipment that you'll take home and do work on your own house. So here we have this DIY variable that somebody has gone through for each customer and characterized them. Yes, this individual buys DIY type stuff, or no, they don't. we have age in categories, and we have the type of home. Is it an apartment or is it a family residence, like a home, a house? So these are not PCA data. PCA is for numeric variables. These are categorical variables. But in a similar way to what we've done with PCA, is it possible to find patterns, associations, structure among these categorical variables that explains a lot of the story in the whole data set? So let me go get the script. diy.r. And come over here and load the data in. So this is the short little script. I'm just going to read the data, and then the package, the package I'm going to use for correspondence analysis is called CA for correspondence analysis. So I'll library that in. There is no package. Okay, so I need to install it. And to apply multiple correspondence analysis, you can just use the MJCA function. And I'll show you the basic output that we can discuss. So here is compute the correspondence analysis representation. Here is what happens if you just print the resulting object. And if you look at it, the output is very similar to PCA type output. There's eigenvalues, and then there's eigenvectors. The eigenvalues are going to tell us about what proportion of the quote story is explained by each of these discovered new variables. And these numbers tell us about the relative contribution of each level of the categorical variables to the discovered new dimensions or new variables. So I'm not going to go through this in great detail, but I just want to highlight that correspondence analysis is like principal components in the sense that we have decomposed a particular matrix into eigenvalues and eigenvectors. So the same way that doing that to numeric variables tells us about the essence of the numeric variables, this multiple correspondence analysis is going to tell us about the essence of the categorical variables. I'll say more about how that's done in just a second, but for now let's look at this picture. This is the correspondence analysis picture for these data. So it's a two-dimensional representation of our five-dimensional data. We have 5 variables at least, 5 categorical variables. And we can say what each dimension represents or what it contributes to the overall variability. The first dimension, this is like a first principal component. It's not exactly a principal component though, but the first like decomposed structural element of these categorical variables explains 73% of the variation among them. And the second one only explains 5%. This is kind of like a principal component plot. When we do principal components, we can decompose our numeric variables down to a small number of principal components. If we pick two principal components, we can say PC1 explains such and such percent, and PC2 explains so and so percent, and we could make a scatter plot. Here's the plot of PC1 versus PC2. There'd be a separate dot for every individual in the data set. Every individual who in the original data set is represented by P numeric quantities has been crammed down to just two numbers. So we've talked about, in a principal component context, looking at the scatter plot of principal components and commenting or learning about the structure among the data. Are there outliers? Are there groupings? Like there's a cloud of points that group together and there's another cloud that group together. So that type of picture is informative. This is like that, but it's a little bit different. If you look at the labels of the points, we've got these red triangles that are the points that have been plotted. And each one of these little triangles is labeled with a level of one of the categorical variables. So for example, DIY is one of our categorical variables. In the plot, there's a separate point for DIY yes and DIY no. So with correspondence analysis, we don't decompose the categorical variables so much as we decompose the levels of the categorical variables. So let me just tell you what you can glean from this picture. 73% of the story is represented by this horizontal direction. So going from the left to the right is very informative. Think about the nature of the data. It's a bunch of categorical variables. You could cross-tabulate all those categorical variables. How many times is it a DIY yes who is somebody who lives in a house who's aged 30 to 45? You can cross-categorize all the categories of these variables. Out of all those cross-categorizations, which categories tend to show up together and which categories tend to not show up together? The most important, or the most informative, or the most frequent source of grouping is represented horizontally. So let's look at what the picture is telling us horizontally. Over here, on the left side of the picture, we have several levels of some of the variables. These are people who own their home. These are people who are between 30 and 45, who live in a house, who are do-it-yourselfers, and who are not skilled and not unskilled. Skilled, I think, might be like a trade type specialization, like plumbing or electrician. Unskilled might be like flipping burgers or mowing lawns. And other, I bet, is like white-collar professionals. So this little grouping of triangles suggests that a big source of the structure of our categorical variables is that these tend to happen together, which is interesting from our perspective as Home Depot, because we can say the people who tend to be do-it-yourselfers are in that age category with that type of home and that type of home arrangement and that type of home. So if I'm thinking in terms of a marketing campaign, let's send out some email advertisements about a sale we're going to have this weekend on do-it-yourself tools. This is the subpopulation that you would want to target more so than some other population. Do-it-yourselfers tend to be this combination of characteristics. On the other side of the picture, this guy is cut off, but I think this is type apartment. The type variable is what type of home. Is it a single-family house or is it an apartment? Over on the far right, we have a grouping, apartment together with rent. To a lesser extent, younger people who are not do-it-yourselfers and who are unskilled, which probably in this case is lots of students. Work skilled and age 45 to 100 are close to the center or the origin, which suggests that those don't particularly associate with the other levels of the variables. I would interpret this picture primarily as this suggests that the biggest source of structure in these data is that there are the do-it-yourselfers who are 30 to 45 who own a home who tend to have these characteristics together. And there's a different population that are the younger, unskilled, not do-it-yourselfers who rent apartments. If we were to go through the data set, we would find many instances of this combination, and we would find many instances of that combination. We wouldn't find many instances of like DIY with age 0 to 30. Because these triangles are on the opposite side of the origin from these, they don't tend to happen together. The vertical direction is much less informative, just like with principal components, we can quantify how informative each of the principal components is. The first one is always the most informative, and the second one is less. Same thing with correspondence analysis, because all we're doing is eigen decomposition again. In this case, the second dimension that was discovered only explains 5% of the story. So this is very subtle relative to this one. The big picture, the big story of these data is that these go together, those go together, and they don't mix. The subtle story, though, is that the skilled workers tend to be young, whereas the older people tend to be the unskilled, no DIY. So what I mean there is that if I'm going to interpret this picture, I'm going to interpret it in two ways. What does the horizontal spectrum represent? What does the vertical spectrum represent? And to answer that, you look at the extremes and who groups together on those extremes. Okay. One more minor thing, or one more quick thing. How does this happen exactly? What is this? How do you eigen decompose a bunch of categorical variables? So what you can do, basically you have to take your categorical variables and you have to turn them into numbers of some kind. The natural set of numbers to play with categorical variables are cross tabulations. So you could take the age category and cross-tabulate it with tenure. How many in the young category rent? How many in the young category own? How many in the middle-age category rent? How many in the middle-age category own? And so on. You could tabulate all the cross combinations. What correspondence analysis does, roughly speaking, is it puts together a giant matrix that contains all the cross tabulations. Every level of these variables cross-tabulated with every other level. So a big matrix of integers. And then it does eigen decomposition with that. That's all it is. It's like PCA type decomposition, eigendecomposition, on the big matrix of all cross tabulations. It's called a Burm Matrix. So in the real world, you have an Excel spreadsheet full of data. Some of your variables are numeric, some of them are categorical. PCA is for your numeric variables. Correspondence analysis is a technique that's appropriate for your categorical variables. There's not a real natural way to do both simultaneously. So I don't recommend trying to fold in your categorical variables into PCA or vice versa. Having said that, some people will use certain types of categorical variables as if they were numeric and do PCA with them, like if you had binary data, zeros and ones, you might use them in PCA. But arbitrary categorical data, I don't recommend giving them arbitrary numbers and using them in PCA. So what I do is with my big multivariate data set, I do PCA on the numeric variables, I do clustering on the numeric variables, I do correspondence analysis on the categorical variables. That's my exploratory analysis of the data. That, in addition to univariate summaries and exploration, like what are typical values, what's the range of values, are there any missing values, are there outliers for each variable individually, is a good template for exploring a data set. And the first thing you should do with any data set before you click buttons to do like p-values and confidence regions and stuff, first thing you do is look at it. The exploratory step is the first step. PCA, correspondence analysis, cluster analysis, those are all exploratory techniques. So where we're headed next, I'll let you go here in 5 seconds, is what I'm going to call statistical learning, and in particular, supervised statistical learning. And I mentioned that book, Introduction to Statistical Learning. Remember that it distinguishes between supervised and unsupervised learning. Clustering and PCA is unsupervised learning. It's just exploratory. It's looking at data. We're going to change gears and attention to supervised learning now, and we'll spend a few weeks on it. That's the task of modeling the relationship between a known response and some predictor variables. For example, let's predict the value of cancer or not cancer based on a bunch of numeric inputs. Or let's predict whether an email is spam or it's not based on a bunch of categorical inputs. Basically, predictive modeling. Let's build a model and use it to predict things. That's where we're headed. And yeah, okay. So I will be here Friday, lecture on that starting Friday. Okay, thank you. Crazy out there. Do you know what class that is? Is that